Hello everyone and welcome to my video. Today we will embark on a fascinating journey of the beginnings of classical mechanics. We will start by exploring Galileo's groundbreaking experiments on inertia, which led to the foundations for Newton's three laws of motion. As we know, Newton's laws of motion form the backbone of our understanding of everyday movement. They describe how objects behave in response to forces, from a car accelerating on the road to a ball thrown into the air, helping us navigate and predict the physical world around us. In the early 17th century, more precisely in 1638, in his book from Italian Discorsi e dimostrazione matematique intorno a due nuove scienze, in English Dialogues and Mathematical Demonstration related to two new sciences, Galileo published his findings from a series of experiments using tilted planes and rolling balls. His objective was to study the motion of objects and understand the concept of inertia. By observing how balls roll down inclined planes and noting that they continue moving even after leaving the plane, Galileo concluded that an object's motion persists unless acted upon by a net external force. Let's delve a bit into the experiments with detail. In the first scenario, Galileo rolled a ball from certain height down an inclined plane. The plane then inclined upwards at the same angle. He released the ball, and he observed that the ball rolled up the second incline and reached nearly the same height from which it was initially dropped. This demonstrated that the ball retained its energy, losing only a small amount due to friction. In the second scenario, Galileo then modified the experiment by reducing the angle of the upward incline on the second half of the plane. When he released the ball, it still ascended the second incline but traveled a longer distance to nearly reach its original height. This further emphasized the concept of inertia, showing that the ball tried to reach the same height despite the change in the angle incline, again only slightly affected by friction. In the final scenario, Galileo replaced the upward incline with a horizontal plane. So, where will the ball go now? He noted that when the ball reached the horizontal section, it continued to roll indefinitely, maintaining a constant speed, as long as friction and other resistances and forces were minimized. This led him to conclude that in the absence of friction, an object in motion would continue to move at constant velocity. This observation laid the groundwork for Newton's first law of motion. These experiments were crucial in developing the concept of inertia and understanding that objects naturally resist changing in their state of motion unless acted upon a net external force. Galileo laid the groundwork by demonstrating inertia through his inclined plane experiments. While these experiments provided crucial empirical evidence for the concept of inertia, Newton synthesized these findings into a broader theoretical framework that included his three laws of motion and the law of universal gravitation. Newton's formulation provided a systematic and mathematical description of motion. Newton's first law underscores the idea that objects naturally resist changing in their state of motion. It laid the foundation of classical mechanics and revolutionized our understanding of motion and forces. The first law states the following. An object at rest will remain at rest, and an object in motion will remain in motion at constant velocity unless acted upon by a net external force. After understanding Newton's first law, which establishes the concept of inertia and states that an object will remain in its state of motion unless acted upon by a net external force, we can now delve into how this force actually affects motion. Newton's second law takes us a step further by quantifying this relationship. It introduces the concept of force as the cause of change in an object's motion. This law can be formulated in terms of linear momentum, which is the product of an object's mass and its velocity. Newton's second law states that the rate of change of linear momentum of an object is directly proportional to the net external force acting on it. Mathematically, this can be expressed as F equals the derivative in time of the linear momentum. This formulation tells us that a force applied to an object changes its motion over time, thereby altering its state of motion. In the general case where both the mass and velocity depend on time, we apply Leibniz rule for derivatives and we get that the force equals the derivative of linear momentum in time. The derivative of the first, the mass with time, multiply the velocity, plus the mass multiplying the derivative of velocity with time. And as we know, the derivative of velocity with time is the acceleration. This is simply the derivative of the mass with time multiplied by velocity plus mass multiplied by acceleration. In the special case that the mass of the object remains constant, the equation simplifies to the well-known form F equals mass multiplied acceleration. In summary, Newton's second law not only introduces the concept of force, but also provides a mathematical framework to understand how forces cause changes in motion. This law is fundamental in explaining how and why objects accelerate when forces are applied. Newton's third law states that for every action there is an equal in magnitude and opposite reaction. This means that whenever an object exerts a force on another object, the second object exerts an equal in magnitude and opposite force on the first object. Newton developed this law based on his observation and experiments on the interaction between objects. He realized that forces always come in pairs. When a body pushes or pulls another, the second body pushes or pulls back with equal magnitude but in the opposite direction. This principle was crucial in forming a comprehensive understanding of dynamics and motion. It is important to note that action and reaction forces do not cancel out when drawing the force diagram of a single body because they are applied to different bodies. The action is applied to one body and the reaction to the other. However, when studying the system of two bodies together, they will cancel out since they are of equal magnitude and opposite directions if we sum the equations for each body separately. Let's look at a simple example that illustrates this concept. Let's suppose we have two bodies in contact with each other and we push the first one by applying a force F with our hand. Experience tells us that both will move together, but if the external force is applied to the first one, how does both two move then? The explanation is that by being in contact, box 1 exerts a force F12 on box 2. Newton's third law tells us that for every action, there is an equal and opposite reaction. Therefore, since box 1 exerts a force F12 on box 2 exerts a reaction on box 1 of equal magnitude and opposite direction F21. It should be noted here that, in the same way, box 1 exerts a reaction on the hand that pushes it, as the hand is exerting a force F on box 1, but we are only investigating what happens at the contact between boxes 1 and 2. That is, we are only studying how boxes 1 and 2 will move, not interested what happens to the hand as a consequence of being the cause of the movement. This concept of reaction is easy to experience in everyday life, as if we, for example, push ourselves a fixed wall, we tend to move backwards. This force that pushes us backwards is the reaction of the wall on us. Let's then solve this situation of the movement of the boxes mathematically. We choose the positive direction of the x-axis to the right. Then the action vector F12 is its magnitude, let's say lowercase f, multiplied by the unit vector in the positive direction of the x-axis. And the reaction force F21 is of the same magnitude as the action F12, that is lowercase f, but pointing in the negative direction of the x-axis. Now let's isolate each box separately and draw its corresponding force diagram. The forces acting on box 1 are the force of the hand pushing and the reaction exerted by box 2 because it is in its front. If box 2 was not there at all, box 1 would move more easily with less opposition. We see that the force with which the hand pushes goes in the positive direction of the x-axis, and the reaction of box 2 goes in the negative direction. Therefore, if we write Newton's second law for box 1, we will have capital F minus lowercase f equals mass 1 multiplied by A1 acceleration 1. Now we isolate box 2. The only force acting on it is the force with which box 1 pushes it, F12, which goes in the positive direction of the x-axis. Newton's second law applied to box 2 leads to lowercase f equals m2 multiplied a2. If we now sum the two equations, something we can always do in this type of algebra, we have that capital F equals mass 1 multiplied acceleration 1 plus mass 2 acceleration 2. And since the two boxes move together without one shifting away from the other, they both move with the same acceleration. So finally we get this is equal to mass 1 plus mass 2 multiplied by the acceleration. Thus, when considering the system of two boxes, the action and reaction do cancel out because they are internal forces within the system. However, they do not cancel out when considering each box separately. We see that what remains takes the form of Newton's second law. The external force on the system, the hand, pushes a mass that is the sum of the two masses of the two boxes and, as a result, acquires an acceleration a. This situation is completely indistinguishable to having a single box with mass m1 plus m2 pushed by the force F of the hand. Isaac Newton's famous story about the apple is often used to explain how he came up with the concept of gravity. During Isaac Newton's time, astronomers had already made significant progress in observing celestial bodies. They could observe the planets, moons, and stars using telescopes, which had been greatly improved by figures like Galileo and Johann Kepler. Kepler's laws of planetary motion, which describe the elliptical orbits of planets, were particularly influential. However, astronomers were still trying to understand the underlying forces that govern these celestial motions. According to the legend, Newton was sitting under an apple tree when an apple fell on his head, prompting him to wonder why the apple fell straight down instead of sideways or upwards. This observation led him to the idea that there must be a force pulling objects towards the Earth. Newton then extended this idea to celestial bodies, including the moon. He reasoned that if the same force that caused the apple to fall also acted on the moon, it would explain why the moon orbited the Earth instead of flying off into space. This insight led to his formulation of the Law of Universal Gravitation, which states that every object in the universe attracts every other object with a force directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Newton's insight was revolutionary because he provided a physical explanation for Kepler's laws by introducing the concept of gravity and the law of universal gravitation. This allowed astronomers to better understand and predict the movements of celestial bodies, unifying the physics of heavens and the earth. Newton's universal law of motion was celebrated as the cornerstone of our understanding of the cosmos until the 20th century, when Albert Einstein came up with his groundbreaking theory of general relativity, making a monumental shift in the world of physics. Here are a few links if you are interested in further reading. Hope you find it interesting. Thanks a lot if you made it this far. Stay curious, practice math. Bye bye.